What we are going to talk about today is the nodal analysis technique. Nodal analysis is simply applying Kirchhoff's current law at multiple locations in a circuit to solve for all unknown voltage quantities. So we are going to analyze a circuit, and then I'm going to walk you through the steps that make up nodal analysis. Okay. So the first circuit that we're going to analyze is this guy. So let's look at a couple of things about this circuit to understand how and why we need to develop more analysis techniques. In this particular circuit, not wildly difficult, there's only 6 elements. However, there are literally no combinations that we could make to simplify this circuit in any way, shape, or form. So what we're going to do is we are going to develop a systematic approach to solving a circuit like this, where there are no steps we could enact. Sorry, my allergies are bothering me again today. Where there are no things that we could do to simplify things. All right. So our first step, number 1, will be to identify our nodes. All right. I'm going to do that just like I did when we were looking at a resistor combination problem. And I'm simply going to color in each different node like so. And we can see that this circuit contains 4 distinct nodes. Okay. Step number 2 is to select a reference or more commonly called ground node. Okay. So typically speaking, I choose my ground node to be the node that has the most elements connected to it. Okay. So if we look at the orange node on the top left, there are 3 elements connected there. If we look at the red node on the right, there are 3 elements connected. If we look at the blue node in the middle, there are 3 elements connected. And if we look at the green node at the bottom, there are 3 elements connected, which means all of these nodes are equally as likely to work as ground for us. The math is going to be just as difficult or just as easy regardless of where we choose our ground. So I'm going to open it up to you guys. Where would you like the reference node to be? Green. All right. So what this selection does is it effectively says that node, the green node, is now at an assumed potential of 0 volts. Okay. So this ground node designation means that this guy is at 0 volts. And our next step, step number 3, is to assign nodal voltages, and I'm going to talk about what that means. Okay. So I am arbitrarily going to call this orange node, node A, this blue node, node B, and this red node, node C. You can use whatever designation you want, A, B, C, X, Y, Z, 1, 2, 3, whatever floats your boat. Nothing particularly important about that. And I'm going to give each of these nodes a voltage. So I'm going to call this VA, VB, and VC. These nodal voltages are the voltages measured with respect to our reference node. So the nodal voltage VA is a shorthand notation for the voltage drop over the 10 ohm resistor, okay? So VA represents the positive polarity terminal of a voltage drop, and ground represents the negative polarity terminal of the voltage drop. So VA is exactly the voltage drop across the 10 ohm resistor, okay? VB then is the voltage drop over the 2 amp current source. And VC is then the voltage drop over the 1/2 VX dependent current source. So we're going to get to this momentarily, but let's talk about that voltage VX up top, okay? VX is defined positive polarity terminal on the right, negative polarity terminal on the left. Well, the nodal voltage associated with the positive polarity terminal is VC. The nodal voltage associated with the negative polarity terminal is VA. So we could say that VX is simply VC minus VA. We'll be able to express all voltage drops in our circuit as a combination of nodal voltages, okay? But inherently, nodal voltages are measured with respect to ground, and the nodal voltage designation is the positive polarity terminal, and ground is the negative polarity terminal, okay? All right, so those are our first 3 steps. On occasion, those 3 steps will be done for you in the problem. So if you see a ground designation, then obviously step 2 is done for you. Sometimes on problems that I give you, I might say, find the nodal voltage V1 or something like that, where I'm telling you explicitly which nodal voltage I'm interested in. Other times you'll have to do these 3 steps yourself. You can easily tell whether or not that's the case just by looking at it and see if they're given to you. If they are, you obviously don't need to do it. If they aren't, you obviously do. Now we're going to get into our analysis portion, okay? So step 4 is going to be express controlling variables in terms of nodal voltages. And I put this as the first analysis step because it is the easiest to forget to do. Okay? So I like to get it out of the way first. So let me explain explicitly what I mean by this statement. If there is a dependent source in the circuit, in this case, there absolutely is, our goal here is to write an equation that tells us how the controlling variable, which in this case is this voltage Vx, because this voltage Vx controls the dependent source. So we need to write an equation that relates that controlling variable Vx in terms of our nodal voltage, or our nodal voltages, which is what we did just a moment ago, right? So we observed that Vx is equal to Vc minus Va. Anytime we want to express a voltage, it's always going to be the voltage, the nodal voltage at the positive polarity terminal minus the nodal voltage at the negative polarity terminal. Always, 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 okay? Just as a brief aside here, I'm gonna show you this and then we're gonna delete it in a moment. But let's say that I had a current like so, IY, that controlled some sort of dependent source. How could we express that current in terms of our nodal voltages? Anybody have any thoughts? IA minus IB, well, what's IA and IB? Right, okay, so we're going to use Ohm's law, where we're going to take the voltage drop over the element expressed in terms of our nodal voltages and then divide it by the resistor value itself, okay? So since the current is flowing from left to right, what we would say is that IY is VA, the node the current starts at, minus VB, the node the current ends at, divided by 5 ohm resistor the current is flowing through. Okay, that's nothing but Ohm's law there. All right. So effectively what we are doing is we're saying the voltage drop across the 5 ohm resistor is positive polarity on the left, negative polarity on the right, based on the direction of the current that's flowing through the element. Okay. All right, so we're not going to actually wind up using this equation, but I wanted to talk to you about how we do it because you're going to be doing a lot of just that. All right. So after we have expressed all of our controlling variables in terms of our nodal voltages, our next step is going to be apply Kirchhoff's current law at all non-reference nodes. So in this case, that would mean we're going to write a KCL equation for node A, node B, and node C, because none of those nodes are the reference node, right? So KCL at node A, what we are going to do is, let's do this in pink. We're going to look at this current flowing down, leaving node A, this current flowing to the right, leaving node A, and this current flowing up, leaving node A, and we're going to add them all together and set it equal to 0, because that's exactly what Kirchhoff's current law is, right? So let's take the current flowing down first. Anybody have any thoughts as to how we can express that current in terms of our nodal voltages? Exactly right. VA minus 0, so I'm just going to leave it as VA, over 10 ohms. Somebody else tell me how to write my equation for the current flowing to the right through the 5 ohm resistor. Hint, it's already on the board. Exactly right. And lastly, I need the current that's flowing up through the 15 ohm resistor. Somebody else. So Vx isn't a nodal voltage, so it shouldn't show up in a KCL equation like that unless it's part of a current source, or really unless it's part of a current source. So the nodal voltage that that current ends up at is Vc. So it should be Va minus Vc over 15 ohms. We set this equal to 0. We had 3 currents leaving node A. There are 3 terms in our KCL at node A expression. So I feel like we're at a good place to stop with that one. Now we're going to move along to node B. So let's see, I'll use this gray color. So we're going to have the currents directed to the left through the 5 ohm resistor, the current directed down, and the current directed to the right. So let's start with the current directed to the left. Who can tell me what that's going to be? Exactly right. VB minus VA over 5. What about the current flowing down through the 2 amp source? Negative 2 amps, because it's flowing in the opposite direction of the current source. And then finally, the current flowing to the right through the 20 ohm resistor. Exactly right. You guys are picking this up very quickly. That's wonderful. There are 3 currents that we're leaving. We've got 3 terms in our equation. We're done with this node. So finally, we'll move along to KCL at node C. And that means we're going to be looking at this current down, this current to the right, and this current up. Davis, how are we going to represent the current flowing down? What's a current source? So it's whatever it tells us. Right? So since this guy right here is in the same direction as our current source, it's literally just half Vx. If it were in the opposite direction of our current source, it'd be negative 1/2 Vx. Okay. We absolutely can do that. So we would have positive 0.5 Vx, which we know Vx is Vc minus Va, so we could absolutely substitute that in. Nick. Exactly right. So let's talk about that very briefly. That is the convention that I have adopted. And the reason that I have adopted that convention, you don't have to do it that way in any way, shape, or form, but I do it that way because I get the least amount of negative signs messing things up. So what I mean by that is if we look at KCL at node A equation, our variable VA always has a positive sign. If we look at our KCL at node B equation, our variable VB always has a positive sign. And when we look at our KCL at node C equation, we're going to find that VC is always going to have a positive sign. The only place that could get messed up here would be the substitution for Vx, right? If I had Vx defined to be positive polarity on the left, negative polarity on the right, that Vx would introduce a negative sign on VC, but all of the currents leaving that node bit, like the currents flowing through resistors, the VC term would still always have a positive sign. All right, so what about the current flowing to the left through the 20 ohm resistor? VC minus VB over 20 ohms, okay? And finally, the current flowing up through the 15 ohm resistor. All righty, VC minus VA over 15 ohms. So if we follow Dylan's suggestion and substitute our controlling variable relationship into our KCL at node C equation, we have a system containing 1, 2, 3 equations and 3 unknown quantities, which means we could use our calculators to solve for it. Now, traditionally here, if you were going to do this by hand, which I absolutely do not suggest that you do, it involves using Cramer's rule, not particularly hard, but it is very tedious, and there's a reason you guys bought calculators. We would need to organize these equations significantly. But our calculators, we don't really have to do that too much, okay? So what I mean by that is if we look at our first equation, the coefficient for our variable VA is going to be 1/10 plus 1/5 plus 1/15, because that's what VA is multiplied by in all 3 terms. So we just lump those guys together. Well, our calculator, we can actually just enter in 1/10 plus 1/5 plus 1/15, and it'll take care of combining all that kind of stuff for us. Similarly, our coefficient for VB would be negative 1/5, and our coefficient for VC would be negative 1/15, right? So I'm going to write down a matrix here, which is effectively what you're going to wind up putting into your calculator. All right. So if we're looking at equation 1, our coefficient for VA is going to be 1/10 plus 1/5 plus 1/15. Our coefficient for VB is going to be negative 1/5. Our coefficient for VC is going to be negative 1/15. And this coefficient matrix, excuse me, is being multiplied by our variable array, VA, VB, and VC, to give us constant terms, which I'm, in this case, the constant is simply going to be here for that first equation. If we look at our second equation, our coefficient for VA is negative 1/5. Our coefficient for VB is positive 1/5 plus 1/20. Our coefficient for VC is negative 1/20. And our constant term would be positive 2 amps. So we would move the negative 2 amps in the middle over to the right-hand side of our equal sign, giving us a 2 that goes here. For our third equation, Our coefficient for VA is going to be negative 0.5 from the VX term. And then we're going to have minus 1/15 from that third term. Our coefficient for VB is negative 1/20. And our coefficient for VC is positive 0.5 plus 1/15. And there are no constant terms. We'll put that in as 0. Okay. If you have a TI 36X, you have a Casio FX 115 or a Casio 991, I can help you figure out how to put these matrices in. Lindsay, I have no idea how your HP calculator works. Okay, wonderful. Thank goodness, because I couldn't even begin to tell you how that thing works. So if we put these into our system solver, 1/10 plus 1/5 plus 1/15, negative 1/5, negative 1/15, 0, negative 1/5, 1/5 plus 1/20, negative 1/20, positive 2, negative 0.5 minus 1/15, negative 1/20, 0.5 plus 1/15, 0, and we solve. What mistake did I make? You're absolutely correct. Thank you. That's the issue there. Thank you so much, Dustin. So what Dustin pointed out is that I missed the plus 1/20 here. And so I'll need to fix that, obviously. There we go. Thank you so much. And solving this system, what we find is that our quantity VA has a value of 16.703 volts. Our quantity VB has a value of 24.835 volts. And our quantity VC has a value of 17.363 volts. Hopefully you all got that. Dustin, thank you so much for catching my mistake. Told you guys I'm going to make them. All right, so we now know what those quantities VA, VB, and VC are. That is the nodal analysis technique. Now let's talk about how it can be applied specifically to do certain things, okay? So obviously we have just figured out what these voltages VA, VB, and VC are. So if I asked you what the power supplied by the 2 amp source is, how could you figure that out? Exactly right. 100% correct. So VB represents the voltage drop over the current source with respect to ground. You're 100% right. The current would be flowing into the negative polarity terminal and out to positive. So the power supplied by the 2 amp source would literally just be 2 amps times VB. You're 100% correct, Devaria. What if I wanted the current flowing through the 20 ohm resistor to the right? I didn't ask for the power. And also that wouldn't be correct either way. The current flowing through that resistor is VB minus VC over 20. This is exactly how we defined it in our equations earlier, right? If we wanted the power absorbed by that 20 ohm resistor, it would be VB minus VA over 20 ohms, quantity squared, multiplied by 20 ohms, or it would be VB minus VC quantity squared divided by that 20 ohms, depending on if we want to express it in terms of the voltage drop over the resistor or the current flowing through the resistor. Once we know our nodal voltages, we can get every voltage drop in our circuit, and using Ohm's law for all of our resistors, we can get every current flowing through our circuit so that we can calculate any power that we would be interested in, okay? So nodal analysis is an extremely powerful tool to figure out all these different voltages, but it can be used to figure out with Ohm's law, effectively every other quantity that we could possibly be interested in a given circuit. So what I would like you guys to do is take a few moments and analyze this circuit. With the goal telling me what the power supplied by the dependent source is. All right, so step 4, meaning express your controlling variables in terms of your nodal voltages. Okay, so what did you, let's identify our nodes, but let's go through the full procedure here, right? So here's one node. Here is a second node. Here's a third node. Which node did you choose as your reference? The red one. Okay, interesting choice, but we can absolutely do it this way. Okay, so I'm going to call this guy here VA, and this guy down here VB. So we have steps 1 through 3 finished up, right? Okay. So step 4, expressing our controlling variable in terms of our nodal voltages. So we want the current flowing down through the 4 ohm resistor because that's what IX is. So what node does the current start at? Right, which has a nodal voltage of 0. What node does the current end at? What's it flowing into? No, what node is it flowing into? Right, which has a nodal voltage of VB. So that would tell us that IX is 0 minus VB divided by 4 ohms, using your convention. From here, we would then apply Kirchhoff's current law at node A. So that would look like VA over 2 ohms plus VA over 3 ohms, excuse me, VA minus VB over 3 ohms plus 1/2 IX is equal to 0. And KCL at node B would look like 2 amps plus VB over 4 ohms plus VB minus VA over 3 ohms minus 0.5 IX is equal to 0. And we have 3 equations, 3 unknowns, so we actually don't even need to do the substitution here to get this to a point that our calculator can solve for. We can solve for VA, VB, and the quantity IX just using our system of equations. Or we could substitute things in and then solve for VA and VB and then use those values to calculate IX. Whatever way floats your boat. So if we solve this system, what we'll find is, take me a moment to do it because you chose a different reference node than me. It's not going to change the value for the power at the end at all. No. So let's see. Set my calculator. So I have 1/2 plus 1/3. And then I have negative 1/3. And then I have half IX, and that's equal to 0. On my next one, I'm going to have negative 1/3, 1/4 plus 1/3, negative 1/2 is equal to negative 2. And on my last equation, I have 0 VA plus 1/4 VB plus 1 IX. One-fourth, and just 1. Solve. So if I punch this into my calculator correctly, I got negative 2.095, negative 3.806, and 0.95 amps. And the power supplied by my dependent source would be 1/2 IX times VA minus VB. I get to be 0.816 watts, which matches the result that I got choosing the bottom node as my reference.
So I believe I understand why we chose IX equals However, for the first example, I don't think I understand EX equals DC.
All right, let's go back to that real quick. So if we are trying to express a controlling variable voltage in terms of our nodal voltages, the equation is always the nodal voltage associated with the positive polarity terminal. So the positive polarity terminal of Vx is associated with the red node, right? Which has a nodal voltage of Vc. The negative polarity terminal is associated with the orange node, which has a nodal voltage of VA. So it's the positive polarity terminal nodal voltage minus the negative polarity terminal nodal voltage, which in this case is simply Vc minus VA. Now, a very common question that students ask is, why aren't we dividing by 15 ohms? And the answer is, if we take Vc minus VA over 15 ohms, that's not Vx. That's the current flowing through that 15 ohm resistor from right to left, okay? So voltage needs to equal a combination of voltages. Voltage can't equal current because that doesn't make any damn sense.
So since the positive polarity terminal is pointing towards VC, it's positive VC.
And the negative polarity is on VA, so it's negative VA. That's it.
So what was the reason in the next example that we chose current to do that?
Because we were trying to find IX, not a voltage, right? So IX is the controlling variable for that dependent current source. So we are doing the same thing. Our step 4s are exactly the same in as much as we are defining our controlling variable in terms of our nodal voltages. In the previous example, our controlling variable was a voltage. In this example, our controlling variable was a current. So that's why we come up with a current relationship. Yeah, so it's whatever's controlling our dependent sources is what we're solving for. Sarah.
So I didn't know about this different way. Instead of doing it in 3 by 3, I just did a 2 by 2 with the substitution of IX into the equation already. Is that still an okay?
Absolutely. Yeah, 100%.
Because it freaked me out when I put it in, because I was the same DB. And then put the power, and I was like, okay, that makes sense.
Yeah, no, 100%. So I don't want to say I don't trust myself to do the substitutions, but sometimes substitutions can get a little wonky. And so if I can solve it without doing a substitution, I'm going to. That's just a personal choice so that I don't make a dumb algebra mistake.
I just did it because in the last week,
Yeah, there's nothing wrong with making the substitution. There's nothing wrong with not making the substitution. Or I could move the IX to the right side, either way. Yeah, absolutely. Any other questions regarding this one? I feel like it's clicking for some of you, and then other of you are still looking a little deer in the headlights-ish, and that's okay. It's going to take practice to get good at this. All right, so what we are about to do is mess things up, so to speak, by including voltage sources, because all of our, I know, I'm such a jerk. All of the analysis that we've done to this point is on circuits that only contain current sources, okay? Voltage sources add in a little bit of a hiccup, all right? So let me explain what I mean by that by looking at a pretty trivial looking circuit, okay? So let's say that we had this guy. We had a 3 amp source. Five ohm resistor. 10 volt source. A 20 ohm resistor. And a 10 ohm resistor over here. So I'm going to identify my nodes. There's 1. There's 2. There's 3. And here's 4. For the sake of argument, I'm going to choose this top right node to be my reference node. Okay. It is an odd choice, so I appreciate your funny look, Sarah. It definitely is an odd choice, but I'm choosing it to illustrate the problem that we're about to see, okay? So I'm gonna make this node VA, this node VB, and this node VC. There are no controlling variables because there are no dependent sources, so I don't need to worry about any of that, right? So now I would simply apply KCL at node A, KCL at node B, and KCL at node C. KCL at node A is just going to be -3 amps plus VA minus VB over 5 ohms is equal to 0. Are we all okay with that? KCL at B, we're going to run into a problem. So I'm going to explicitly show you what's messing up here. We have this current flowing to the left through the 5 ohm resistor, which is well defined in terms of our nodal voltages. We have this current flowing to the right through our 20 ohm resistor, which is well defined in terms of our nodal voltages. And then we have this current flowing down through our 10 volt source, which has no relationship to our nodal voltages whatsoever. Because for a voltage source, the amount of voltage that's being supplied by it is a fixed quantity, and the amount of current that's flowing through it is whatever the hell needs to flow through it to make the rest of the circuit work, right? So what I'm going to do is I'm going to call this current IVS down. Okay. So that KCL at node B would be VB minus VA over 5 ohms plus IVS down plus VB over 20 ohms is equal to 0. When I apply KCL at node C, I'm going to run into a very similar problem, right? So I'm going to have this current flowing through the to the left, which is obviously just 3 amps. This current flowing to the right, which is just going to be VC over 10 ohms. And then this current flowing up, which I'm going to call IVS up because I have no way to express it in terms of my nodal voltages. Okay. That's going to look like 3 amps plus IVS up plus VC over 10 ohms is equal to 0. Okay. So if we look at our KCL at node B equation and our KCL at node C equation, we can see that it contains that current that's flowing through that voltage source in both directions. So what I'm going to suggest that we do is we add those two equations together so that those currents cancel each other out, right? Because IVS flowing up will exactly cancel out IVS flowing down. Now let's talk about why we can do this. KCL at node B is equal to 0. Some of the currents flowing out of node B add together to be 0. KCL at node C, the sum of the currents flowing out of the node equals 0, and 0 plus 0 is equal to 0. So I can add those two nodes together and form what's called a supernode. All right, so what I'm going to do is I'm going to just enclose these two nodes together. Anytime I have a voltage source, I'm going to have a supernode. And effectively what I'm doing here by adding these two relationships together is applying KCL at supernode BC, where we just add the currents that leave the supernode. So This current leaves the supernode. This current leaves the supernode. This current leaves the supernode. And that current leaves the supernode. And then the current IVS down is exactly counteracted by the current IVS up. And so we don't even need to bother to include it. So effectively, draw a circle around your voltage source and then figure out all the currents that are leaving both terminals of the voltage source. That's it. So that's going to be VB minus VA over 5 ohms plus VB over 10 ohms plus 3 amps plus VC over 10 ohms is equal to 0, right? Thank you, you're right, VB over 20 ohms. My apologies. Let me erase that because it looks terrible. So I'm going to scratch these guys out because we're no longer using them. We've lumped them together into a single expression, okay? So the problem that we have now is that we have 2 equations and 3 unknowns, okay? So we need to get another equation. Well, right now, our supernode contains 2 nodes, but it's only giving us 1 equation. So that's where we're going to look for our other equation at. The voltage source tells us that there is a 10-volt difference between node B and node C. That's our last equation. It's a voltage relationship equation. Where 10 volts is equal to the nodal voltage at the positive polarity terminal minus the nodal voltage at the negative polarity terminal of our voltage source. Garrison, which nodal voltage is at the positive polarity terminal? Which nodal voltage is at the negative polarity terminal? So what's my 10 volts is equal to? Absolutely right. And I now have 3 equations, 3 unknowns that I can use to solve my system. All right. So just for completeness' sake, let's go ahead and do that. So let's see, on our first equation, we have a coefficient of 1/5 VA, the coefficient of -1/5 for VB, no VC, and our constant term is +3. In our second equation, we have -1/5 VA, 1/5 plus 1/20 VB, 1/10 VC, and our constant term is -3 amps. And in our third equation, we have no VA, 1 VB, -1 VC, and this is equal to 10 volts. And when we solve, I get 65/3 of a volt for VA, 20/3 of a volt for VB, and -10/3 of a volt for VC. All right. So now that we understand the concept of a supernode, anytime we have a voltage source, we're going to have a supernode. Okay, we just put a circle around it and sum the currents leaving. We are going to work a more difficult problem, and we are going to amend our steps in our nodal analysis algorithm to include what to do when we have voltage sources here, okay? All right, so the circuit that I'm about to draw is gonna look absolutely terrifying to most of you, okay? But I promise the same simple steps that we've been using are exactly what we're gonna apply here to get the answer. So our circuit of interest is gonna be this guy. We have a 4 ohm resistor. We have a 2 ohm resistor. We have a 3 ohm resistor. 6 ohm resistor. An 8 ohm resistor. Up here, we're going to have a dependent voltage source where the voltage depends on 5 times the current Ix. Here we have a 0.4 amp source, short circuit, 10 ohm resistor through which a current Ix flows. Volt source, 5 ohm resistor, Ix dependent source, 15-volt source. So this is our circuit of interest. And our goal here is to determine the value of the quantity Ix. Okay. So step 1 is still going to be identify our nodes. So we have this top left node, this top right node, this left middle node, this center node, this middle right node, and this bottom node. So 1, 2, 3, 4, 5, 6 nodes. Right? Are we all comfortable with identifying our nodes? Okay. Our next step is still going to be choose our ground. I am going to choose the bottom node as ground, okay? Now, and I'm going to explain my reasoning for that in just a moment, okay? So bottom node is ground. This bottom purple node has 4 elements connected to it. Now, the blue node in the center has 1, 2, 3, 4, 5, 6, 7 nodes connected to it. So that would seem like the more obvious choice, okay? When I have voltage sources in my circuit, I choose my reference node based on which one touches the most voltage sources. And the reason for that is going to become obvious when we get to our KCL equations, okay? So since the bottom node touches 2 voltage sources, That's why I chose that one in particular. You could work it with any node chosen as your reference. It'll just make some equations more difficult to write, but it's not anything wildly complicated. Okay. Step 3 is to label our nodes. So I'm going to call this guy node A with a nodal voltage VA, this guy node B with a nodal voltage VB, this guy node C with a nodal voltage VC, this guy node D with a nodal voltage VD, and this guy node E with a nodal voltage VE. So our first 3 steps are absolutely the exact same thing that we did previously. Nothing new has been introduced. Step 4 will also remain unchanged. So step 4 is to express controlling variables in terms of our nodal voltages. So in that case, that would be expressing the current Ix in terms of our nodal voltages. Who wants to take a crack at that? Exactly right. VD minus VE over 10 ohms, 100%. Both of our dependent sources are controlled by that same variable, so we only need to write one equation here. So now we go on to step 5. So this is where we're going to have something different. Before we move along to our KCL expressions, we are going to write voltage relationship equations for every voltage source. So let's start with the 15-volt source. What's the nodal voltage associated with the positive polarity terminal? VC. What's the nodal voltage associated with the negative polarity terminal? Or 0. So from that, we can say VC is 15 volts. We have effectively eliminated an equation. That's why I chose ground to touch voltage sources. What's our voltage relationship equation for our 9-volt source? Just equal to VD. Okay. Lastly, I have our 5Ix voltage source up top. So what's our voltage relationship for that guy going to be? VA minus VB is equal to 5Ix. Okay, so yes, ma'am. It absolutely does. Okay, so for instance, if the 15-volt source were positive polarity on bottom, then we would have VC is equal to negative 15 volts, because it would be ground minus VC is equal to 15 volts. All right, so what I'm about to do here is I am going to encircle my, in this case, it's what I'm going to call a super duper node for lack of a better term, okay? So I'm going to do the first one here in gray. And so there's a super node formed between node D and ground. So anywhere that I have a voltage source, I form a super node, okay? So here's my super node between VD and ground. There's also a super node between VC and ground. Like so. So that's our super duper node. And then we have a super node formed between nodes A and B because there is a voltage source connected between nodes A and B, okay? All right, so here's something that students seem to miss a lot, so I want to state it very explicitly. When the supernode contains ground, we do not need to write a Kirchhoff's current law equation for that supernode, which means we are going to get no KCL equation for that big ugly blob I've drawn on the bottom. The supernode up top does not contain ground, so we are going to have to write a KCL equation there, okay? So step 6 will be write a KCL equation for all supernodes that do not contain ground. So in this case, that would be a KCL at supernode A, B equation, which would be this current plus this current plus this current plus this current plus that current. So let's start on the left-hand side and work our way to the right. What's the current flowing down through the 4 ohm resistor look like? Exactly right. VA minus VC over 4 ohms. The current flowing, sorry, I went slightly too far, down through the 2 ohm resistor. What's that going to be? VA minus VD over 2 ohms. Absolutely correct. The current flowing diagonally down through the 3 ohm resistor. VA minus VD over 3 ohms. Absolutely right. The current flowing down through the 6 ohm resistor. VB minus VD over 6. Thank you. And lastly, the current flowing down through the 8 ohm resistor. VB minus VE over 8. All righty. That's our only supernode that doesn't contain ground. So we're on to step 7. Write KCL equations for all other non-reference nodes. So we have our KCL equation for supernode AB taken care of. We don't need to write a supernode equation for supernode VC, supernode C, D, and ground. So the only node that's left is E on the right-hand side. That's just going to be this guy plus this guy plus this guy. So what's the current flowing up through the 8 ohm resistor look like? E minus B over 8. What's the current flowing to the left through the 10 ohm resistor look like? VE minus VD over 10. And lastly, the current flowing down through the 5 ohm resistor. VE over 5. All right, so what I want to do here real quick is count things up, okay? So in our original circuit, we have 5 unknown nodal voltages and a controlling current IX. So that's 6 variables. Here's equation 1, 2, 3, 4, 5, and 6. 6 equations, 6 unknowns. If you do these steps in this order, you will not forget any of your equations. Okay? That's one of the most common mistakes that I see people do. They set things up effectively doing steps 1 through 3, and then jump down to the bottom and start writing their KCL equations, and then always say, well, where are my other equations supposed to come from? They came from the steps that you skipped, where I explicitly told you these are the easiest ones to forget. So write them first. Always write your controlling variable equations first, then write your voltage relationship equations, then get into your KCL, and you're guaranteed you're not going to be missing anything. All right, so this is a 6 equation, 6 unknown system. Obviously, there are substitutions and things like that that could be made. Realistically, I wouldn't bother with the substitutions. I would use a program like MathCAD to just solve all of them simultaneously. We're running a little bit short on time, so I'm not going to give you guys a MathCAD example today of solving this, but I will make a video using MathCAD, setting things up and all that kind of stuff and post it online. In fact, I'm just going to be lazy and go find one that I've already made and then put it up there. The homework assignment, some of the problems are gnarly. I can think of, I think homework number 6, problem 7, winds up being an 11 equation, 11 unknown network because the person who made that homework set is a sadist, in my opinion. And he no longer works here, so I can say that without repercussions, I hope. It's somewhere in San Luis Obispo, California. Fantastic question, Nick. So the TI-36X and the Casio 115 are capable of solving systems of equations with a maximum size of 3 equations, 3 unknowns. The Casio 991s can do 4 equations, 4 unknowns. So on your exams, the largest system of equations that I can expect you guys to solve is going to be a 3 equation, 3 unknown system. Those of you that have the Casio that can do a 4x4 system are at a slight advantage, but it's really kind of trivial because one simple substitution will get you down to a 3 equation 3 unknown. So that's the biggest thing that I can expect you to actually give me a numerical answer for. Does that resolve the question? Yeah. I don't know the system solving capability of the HP calculators because Lindsay is the first person I've ever seen use one. How many can it do? 3. Okay, great. For those of you that are using Casio 30, please, for the love of God, buy a less shitty calculator. It's really going to make your life way easier when we get to complex numbers. I have no idea how many equations it can solve, but I know for a fact that it's garbage at doing complex number manipulation, and we're going to be doing a whole heck of a lot of that in about 3 weeks. So spend the $12 to $15 or whatever and get a less shitty calculator. All right, that's enough out of me for today. So you've got roughly 25 minutes to work on the in-class assignment. I hope you'll get one of them done in that time. Sorry for talking so much. I'm being very flippant, sorry, about buying a less crappy calculator. If for whatever reason financially you're not able to do so, I have a horde of calculators. I think I have 3 TI 36Xs, 4 Casio 115s, and 1 Casio 991 if anybody needs to borrow one. Really for the entire quarter, doesn't bother me a bit. As long as you leave me with one of my TIs, I'll be good to go. Apparently, Dr. Swanbaum also sells them at a discounted rate.